Okay, so this is a very introductory lecture on sensors and which will be later on followed by introduction to actuators. Now, the reason why we need this is that as Professor Ogai had shown in the last presentation, that in order to have a pi filth monitoring robot functional, you should not only have the robot driving, but you should also have the robot equipped with various types of sensors, okay? And also at times this needs the actuators. So, that is what brings us to the context of sensors and actuators, and the first thing that we will tackle today are the conventional sensors. Then in my next talk I will talk about smart sensors which are more readily integrable to the system. So, when we talk about the sensors, if you think of a little bit of a case history, the development of the automobile is one very interesting vehicle with which the sensor development is very much actually related. Till 1960, radio was the only electronic system in an automobile. Okay? There was all the gadgets that you see today was not there before 1960, as you can see, and this is one of the those days very classy models of an automobile with only electronics. Engine system, for example, was entirely controlled mechanically at that point of time. But something happened during 1960 to 70, mostly it is due to the environmental pollution. There are so many automobiles, and then they started to have emissions that had actually created a huge pollution in many of the cities. So, there started to be a severe control of the emission of automobiles. Now, if you have to control the emission, you have to control the ignition process. So, there is a electronic ignition system that was introduced, and the moment you have to introduce a electronic ignition system, for a 4-cylinder engine, you have to know what is the position of the crankshaft at any instant, what is the position of the camshaft at any instant, what is the air flow rate that is happening, what is the gas that coming out. So, you have to measure the NOx and all other emission characteristics. So, you need gas sensor at the exhaust, you need a throttle position sensor, you need overall microcontroller to control the ignition. Okay. So, here is a site auto.howstuffworks.com. if you wish to see that how these things are sensed in an engine today, you can actually check it in this particular site. So, essentially the moment we have to have the quality control in terms of the engine output, immediately so many sensors come into the picture. So, this is you see one such classical case where the sensors became integrated to a mechanical system. Now, post 1970, the ABS anti-lock brake device got designed, where the sensor actually senses the locking of wheels and modulate the hydraulic pressure to minimize the sliding. So, this is during the braking time itself, and mid 1990 there came the traction control system, where you are not only controlling it during the braking time, but you are actually finding out what is the acceleration during slippage, and accordingly you modulate the power itself to prevent such kind of slipping. In fact, there are now new concepts of vehicle dynamic control like VDS, millimeter wave radar technology with GPS, which is mostly used during the parking, and you may also see some of the things from Professor Ogai's lab, which is used in terms of platooning of the vehicle. So, which constantly needs sensing of the two vehicles relative position and velocity, etc. So, thus the journey that you can see that started fast with the engine control, and later on with the braking control, and then with the traction control, and then with the platooning etc. Okay, safety position is going to be the same journey for pipe health monitoring robot. Okay. If you look at the initial models of pipe health monitoring robot, okay, they are simple propulsion type, peak type what we say, and gradually when we are making the new models, we have to now think of course, this something similar to anti-lock braking, the slippage should not be there. We have to now think of the traction control of the system, okay, and we have to think of that how you can take it without disturbing the gas flow. So, there will be these series of platoonings or developing it in terms of modules, and also there will be things related to the continuous position guidance etc. So, all these things what is happening to the technology today. In fact, another very important thing which we have not discussed in the last lecture is that when you are actually taking the robot out of the system, the exit point, okay, if suppose it is traveling at a very high speed, that exit point to save it from the impact, that itself would need a special braking technology. So, that it does not harm the robot which is equipped with so many sensors. Okay. So, once again all these technologies will be gradually getting integrated to our system as well. And this is graphically showing that started with emission control, safety systems, then anti-lock brakes, airbags, fuel injection, cruise control, vehicle system optimization like stability control, powertrain, electronic replacement of mechanical systems, and then vehicle optimization, integration of vehicle system, anticipatory technology, connected technology, integrated processor, software dominance. We have just started to develop similar things in the pipe health monitoring domain as well. So, it is a good parallel between the two technology. Now, coming back to the sensors and actuators which has to be integrated to achieve this. What are the sensors? Sensors are something that when it gets exposed to a specific physical, chemical or biological exposure will produce a significant output signal. It could be electrical, it could be mechanical, optical, acoustic, okay, but it has to be of a significant level. There is something called a signal to noise ratio in any transducer. Okay. So, if there is a small change, many material would respond to that small change, but this change will be significantly high in some materials in comparison to the others. Okay. For example, when we will talk about the smart sensors, we will talk about piezoelectric material. Now, there are piezoelectric materials which were invented 150 years before, okay, but they are not as responsive or as sensitive, okay, as you are getting the today's piezoelectric materials. The Rossel salt or the sugar crystal, they are piezoelectric, but their signal to noise ratio is very low, in the sense signal is almost equivalent to the noise in comparison to the type of piezoelectric material that we are using today, like macro fiber composites or active fiber composites. So, it has to be significant. Okay. The other point is that you may not always get a conversion directly from mechanical to electrical. You may get a conversion from mechanical to optical or acoustic etc., and then you can think of further conversion of the system. Now, actuators are just the reverse. That means, it takes an electrical signal and it produces mechanical force, motion, heat flow etc. So, whatever we will see in the sensor domain, in some cases you can actually convert that into the actuator domain. But since both of them essentially works as a converting agent of energy from one domain to the other. So, they are generally called transducers. Okay. So, transducer is the common name for them. So, there are two types of transducers. One is the passive transducer, which will convert the mechanical to electrical energy, or suppose mechanical to magnetic to electrical energy. And the passive transducers do not need any external energy supply. Okay. There are for example, passive transducers which are energy harvesting or energy scavenging. That means, there are lot of energy available in the ambience itself. So, it can extract such energy, okay, and then it can use that energy for the sensing. Actually, sensors are always in the low power domain. Okay. So, for example, breach health monitoring, Professor Ogai is working on one such application, where we have thought of putting piezoelectric systems which can actually get the vibrational energy from the ambience, convert it to electrical energy, and use that electrical energy to charge the sensors, and then carry out a wireless sensor network to take the signals out and develop a complete health environment of the system. So, that is what is the passive transducer. On the other hand, the active transducers actually need power supply. Okay. It may be in the form of the AC or the DC power supply depending on the application, but active transducers need power supply. One example I will show you later is the strain gauges, where you must have a power. Now, there are broadly three ways to look into a sensor. Okay. One way is that you consider it as a phenomena, because I told you that energy transformation is what occurs in a sensor. Okay. So, suppose you consider resistance change as a phenomena, okay, which in a very broad way is actually a product of current times the impedance in the system. And this is like a variable resistance, okay, system. So, if you change this position, okay, the resistance change comes in the form of change in the output voltage of the system. Now, that is something that has many uses. So, once you consider that it is the resistance change that I am going to use, one use could be directly in the form of potentiometers, pots, which we use for all these fans, etc., the speed control, right. So, potentiometers is one such use of resistance change, and there are 2 or 3 direct uses that you know of. For example, the angle sensing, where the potentiometers are made to be able to rotate many times, not necessarily only 360 degree, something like this, that instead of linear you can have an angle sensing. So, as you are going to various points, you are actually sensing what is the output voltage, okay, corresponding to that much of area for which the resistance change is happening. So, you can do it in a circular mode, you can do it in a linear mode, and that means that you can use it for angle sensing, you can use it for linear displacement sensing. Not only that, if you know the distance beforehand, okay, and you know how much of angle you are changing, you are sweeping, you can actually find out the velocity, and you can also find out the acceleration from it. So, you can find out the linear speed or the rotary speed or the counterpart of it, that is the linear acceleration or the rotary acceleration. So, thus a simple resistance change can be used in terms of all these displacement, angle, speed sensing, etc. Not only that, just think of various applications of it. Many of you now work on Ldrs, right. So, you have this cadmium sulphide cells, which is these CDS cells, in which if there is a change of resistance, it is light sensitive, right. So, if there is the change of light, that means because of shading, etc., there is a change of resistance in the system, and you try to see that output in terms of change in voltage. So, this is another example of the application of change of resistance. Microphone technology, where you have small carbon granules, in which if there is a change of pressure, there is a change of resistance, and hence you can use it in terms of signal processing. So, that is another application of these the change of resistance itself. strain gauge, it is nothing but again a resistance change system. Okay. So, what you have in a strain gauge is that you have a material which is very sensitive to small displacement, and these displacements happen because of the change of stress in the system. So, it is very sensitive to small change in it, and that small change creates a change of voltage, but it is difficult to see this voltage directly. What you need is some kind of a Wheatstone bridge to amplify the effect. This is why this kind of a resistance change based system is an active system. You need a power supply to it. There is a passive version of this whole thing, that is known as piezo resistors. Okay. So, in the piezo resistors, what happens is that the piezoelectric crystal actually generates the voltage, and depending on the stress, the piezoelectric crystal will change its resistance, hence that would affect the voltage generation itself. So, you can directly use the same crystal for the change of pressure and creating a change of resistance, and that creating a change of voltage generation. So, that is a active passive counterpart of the strain gauge device. Thermistors, for example, okay, they are sensitive to temperature. So, the change of resistance in this case is something which is like a Joule effect, okay, that changes its variations with respect to temperature. Okay. So, that is what is used in the case of thermistors. Here once again there are many metals which actually with respect to temperature changes its phase, and as it changes its phase, its resistance changes. So, essentially you can use it in terms of a thermal sensor, because the temperature is changing the resistance and that is changing the electrical output of the system. Okay. So, we have talked about two classifications. One classification is based on the effect, okay, and the other classification in this case is based on the function itself. Okay. That means, what function you want to use. For example, I want to sense the linear or the rotational motion. Okay. So, it is not a phenomena that you are using for variable applications, but it is like you have a purpose and you are looking for various sensors. From that point of view, Lvdt or Rvdt are the first names that will come to you whenever there will be a linear or a rotational sensing that will come into picture. Okay. So, in this case for both of them, it is the change in magnetic field that will produce the voltage. You can also think of optical encoders, okay, where you can actually change the digital output of a system because of the angular or the linear displacement. You can of course think of resistive devices. You can think of Hall effects, for example, okay, which is based on a change in the magnetic field. So, here we have a function in mind, and there are various types of sensors that will suit our purpose. Of course, we have to see two things when we will be choosing a sensor. One is that what is the accuracy of the sensor, and another is what is the precision of the sensor. Okay. And other than that, we have to also look into the signal to noise ratio and the range of the sensor, but accuracy and precision is very important. Lvdt gives you some range of accuracy, and optical encoders give you a much better range of accuracy. Similarly, Hall effect gives you even better range of accuracies in the system. So, how does an Lvdt work? Here you have actually a primary coil system, as you can see here, and a pair of secondary coils in the two sides, and you have a plunger, and this plunger has to be physically displaced. Okay. So, there has to be some kind of a mechanical force which should be able to create a physical displacement, otherwise Lvdt system would not work. Now, initially the primary coil and there are these two symmetric secondary coils, they are perfectly in in such a manner that if you apply any voltage in the primary coil, okay, suppose it is in the middle position, you are applying any voltage in the secondary coils through transformer, the voltage that will be generated is absolutely symmetric. But the moment these central plunger is shifting during the displacement, what will happen is that one secondary coil will actually get more core area and another one will get less core area, and immediately there will be asymmetry in the voltage generation. Okay. So, it is a simple system, but it is very effective in terms of and it is very robust actually. So, this is what if the function of a Lvdt sensor. Let us just go to the next sensor, which can also sense the position or the velocity. The one that is known as proximity sensor is nothing but a capacitance based sensor. So, what do you have in a so called proximity sensor? You have two parallel plates there, and you know that the capacitance of the this system, two parallel plates, depends on what is the overlapping area, okay, between the two capacitor, what is the distance between the two capacitor, and of course, what is the so called the permeability of this particular medium itself. So, with these three points, you can actually develop various types of parallel plate capacitors. If you look at the capacitance of the system, then you will see that you have the permittivity of the system, okay, and then the common area and then the plate separation distance. Okay. So, if you have a situation where these, because of the relative separation, this area is changing, you get a change of capacitance, which can be actually used in terms of change of voltage. If on the other hand, you devise a system where the distance is changing between the two, then that will inversely affect the capacitance and that will affect the voltage. Or if you can somehow change the dielectric constant of the system. Okay. There are also sensors which can do it by actually changing the medium with respect to some kind of gaseous flows. You can actually change the dielectric constant and thus you can change the capacitance of the system. So, this is another one like Lvdt, which can be used for position displacement sensing. Okay. And this is usually much more effective and much more sensitive. The only thing is that it needs the presence of two parallel plate capacitance systems. So, you must have two conductors with you. The next one, which is very important, is in terms of position sensing. Okay. Because you know that many a times when a Pfeiffer monitoring robot gets stuck, you do not know where exactly the robot gets stuck. For thousands of kilometers it travels, and then unless you can identify the position, you cannot destroy the pipeline entirely, okay, to in search of the system. Now, let us look into position, because I know many of you are working on radio transmission systems or sonic communication systems, some of which I will cover in the advanced lecture. But let us look into the world of possibilities globally, which may give us some new ideas in terms of position sensing. So, I have intentionally chosen this slide where actually is the migrating birds, how they sense the position. Let us look into that. Okay. So, you get some fresh new ideas from biological perspective. You look at the case history of the navigating birds. Okay. How do they know where their positions are? These golden plovers or the Arctic terns that I had shown you in the last slide, they navigate thousands of miles from Arctic to Antarctica, 22,000 miles in a round trip in the case of the Arctic terns, okay, without ever getting confused between their routes. Okay. They fly by day or by night, it does not matter, and over featureless seas many of the times, oftentimes out of sight of land and above cloud layers. Okay. So, but still they make it. The question is how they make it, how do they navigate. Well, the easier answers are through the landmarks like the homing pigeons, but that is within only about 20 kilometer. Okay. So, we have thought of landmarks in the context of pipe health monitoring robot, right, that we thought of that there must be always welding joints and the pumping stations. So, each welding joint and the pumping station can be used as a landmark. Okay. However, this can be used very locally, not in a global sense. Sun compass, birds flying in daytime can use the sun as a directional cue. Okay. For example, you know that in the fall time the sun at 12 is directly at south in the northern hemisphere, the more you go towards the Arctic side, and it moves about 15 degree per hour. So, that at 2 p.m. south is 30 degree left. Okay. If you have a transparent pipeline, you can make use of it, right. Constellations, most long distance migration occurs at night, but starts at dusk. So, sunset point can be used as an initial orientation point. There could be even more difficult ways, for example, the pattern of polarization of light. This is something that we have not thought of, that light invariably gets polarized, okay, and that pattern of polarization changes with respect to the direction itself. So, this is this is something that the birds use. Stellar navigation with the help of constellation and the motion of the constellation. Okay. Even it is found that inside a planetarium during periods of migratory restlessness, they can actually sense the axis of rotation of the stars. Okay. Now, that brings us to a suspicion today that they may be using the magnetic cues. Okay. That means, must have a magnetic sense, which is very widespread not only in the birds, but in many vertebrates like sharks, rays, alligators, sea turtles. Okay. And this magnetic cue, if you look at it, that it could be because of many reasons. One is of course, what they say that the bird's eyes are actually aligned with surrounded by many magnetic dipoles. So, there are small iron elements which works like magnetic dipoles, which senses the earth's magnetic field. Okay. And then based on that, the intensity of the earth's magnetic field, it detects where exactly it is present. Okay. On the other hand, in terms of vertebrates etc., they have a good amount of iron flowing in the circulation system itself, and that iron moving iron pigments actually generate a magnetic field, because it is subjected to the earth's magnetic field, and you have a moving iron magnet system. So, it is generating some kind of a flux change, and the nervous system can pick that flux change. So, this gives us a clue that magnetic cues could be a good idea. We are using magnetic flux today in the context of pipe health monitoring robot, but for only damage detection, but we have not thought of our position determination with the help of the interaction with the earth's magnetic field, which can tell us that where exactly we are. It is also seen that for the caged birds a very similar phenomena occurs, which suggests that because of the presence of the metallic cages, they may actually get this magnetic sensing, they may get confused in the magnetic field. So, this comes to the broad question that what is it that you need in terms of a position sensing. Now, in a small scale you need two information. A is that what is the distance from a fixed position, and B is that what is your direction. Okay. So, these two things together you will be uniquely able to identify what is your position. If you are in an air navigation system, then you need even more information like altitude, height and spatial coordinates. This becomes important because we are talking of new generation of health monitoring robots, which will not be crawling anymore, right. We are talking of flying robots, which will go through the like an unmanned aerial vehicle, it will go through the flow system. Okay. So, you need actually more information for the stability and the position determination of such a system. Now, this position also refers to distance which can be obtained from velocity and acceleration, right. So, if I integrate acceleration, I get velocity, if I integrate velocity, I get the distance. The only thing is that in this case, you need to also have the integration constant with you. That means, you must a priori calibrate your system such that for known velocities, you have a solution that gives you the integration constant, and similarly for known distances, it gives you the integration constant. So, from acceleration, you can make out what is the distance provided you know these two values, or from velocity you can get distance provided you know that what is the integration constant. Okay. So, what are the methods of direction sensing? Magnetic compass, sextant plus chronometer, both of them is not possible in this particular case. Then the Hall probes, okay. You can seriously think of the Hall probes, the gyroscope and the tilt sensor. Tilt sensor is possibly the most practical one, and towards the end I will ask you, you keep thinking about it, what is the sensor that you think we can use for position sensing. Now, what is the Hall effect sensor? Broadly speaking, this comes into picture when the flow of current takes place not through a wire, but through a strip, like this is a strip from which the current is flowing. So, if the current flows like this, then there will be a displacement of charge across the flow of the current. So, the magnetic field and that happens, that changes this displacement if the magnetic field changes. Okay. That means, if there is a generation of a constant magnetic field which is there with us like the earth's magnetic field, and if you have a current which is passing through a strip, then as the magnetic field is changing, the displacement is changing, and that means I can constantly locate the position of the system. In fact, the voltage that gets generated from such a system depends directly on the current that you are passing, depends on the magnetic field, and inversely depends on the charge density. The electron charge of course is constant, and the thickness of the strip. So, this is what is our Hall effect sensor, which can be used for position detection. The other interesting one is a gyroscope. What happens in a gyroscope? Whenever you are giving an angular momentum, as you can see, it is the Newton's law of inertia that the system, and that is valid not only in a translatory system, but also in a rotational system, that this whole system will try to preserve this angular momentum. Okay. So, if you make any small changes, it will try to come back to this location. Now, then if there is a change that indeed occurs in the system, by measuring that how much of effort is needed to coming back, you can actually measure what is the displacement that has occurred to the system. That is what precisely is used in the gyroscopes. There is a even better gyroscope which is used now for fighter aircrafts, that is called the Sanak effect based optical gyroscope. So, like the gyroscope measures the mechanical resistance that happens whenever there is a change of position, in this case what happens is that you have an optical laser source which is getting beam split. One beam is travelling in a clockwise manner and the other beam is travelling in a counterclockwise manner. Okay. Now, depending on the direction of rotation or the motion, one of the set will be towards the rotation of the laser and in the other one will be against the rotation of the laser. So, hence there will be these two counteracting ones. So, there will be slight shift between the two lasers, and that slight shift between the two lasers will be reflected in terms of interference, etc., from which you can very accurately measure the speed, rotational speed, and hence by integrating the displacement or the direction of the system. I told you that this is the simplest way to find out the tilting, okay? And that is if you have a fluid and 3 electrodes in it. Okay? Depending on the level of tilting, what will happen is that the area of the electrode that is covered by the electrolyte will change between, will be different between AB and BC. So, initially if there is a 0 tilt, then the voltage that will be generated between AB and BC will be same. But as there is a tilting, the voltage that will be generated by AB will be much higher than the voltage that is generated by BC. Okay? So, by measuring this tilting that is happening in the system in terms of a voltage, you can actually continuously keep record of that how you are moving the system. Okay? And if you can keep this history in a memory, then you know what is the path that you have actually tracked. Now, so far we have talked about all the directional sensing techniques. Okay? So, let us just try to think of it that we have talked about the Hall effect that we can use for directional sensing, the gyroscopes that we can use for directional sensing, the optical gyroscopes that we can use, the tilt sensing that you can use, okay, for the directional sensing of the system. Now, let us spend some time on the distance sensing itself. The common combination for distance sensing, which is used in Japan in a very broad manner, is through radar and the sonar. Okay. So, that is in the long range. If you in the shorter range, if you want to use, you can use radio beacon 1 meter to 100 meter. In a very smaller range, we have talked about Lvdt 0.1 millimeter to 1 meter, or capacitance based sensor 1 millimeter to 1 micron meter, or potentiometer or optical encoders. So, how does this radio beacon plus ultrasonic system works? So, here is like typically this is used for wherever you have many robotic modules in a place. What you do is that you have a transmitter here which transmits the radio pulse and the acoustic pulse, and you have a receiver here, and the receiver sends back the signal. Now, in case of a radio pulse, there will be no time difference because the light speed is very very high, but the ultrasonic one or the acoustic pulse is medium dependent. So, that means if you are far away, then there will be a time delay. So, by measuring the time delay between the radio pulse and the acoustic pulse, you know that what is the distance, how far away the system is. Okay? So, that means you imagine that you have a situation where you have from one stationary location like a pumping station, you are sending 2 beams continuously. You are sending a radio emitter and you are sending acoustic emitter. Radio emitter should reflect back instantly, and the acoustic emitter should take a longer time depending on the distance, and thus by measuring the lag between the two, you should be able to find out where you are. Okay? The only thing is that I think in a bend it would not work very effectively, right. That is the only problem, that the radio signal in a bend the loss is substantial. If you have a straight pipe, this should work in a very effective manner. But of course, I thought of systems where you have modules of these robots, okay, they are traveling. Now, each one can measure the relative distance with the next one. That can be done like a platoon. What you think of the platoon in the real automobile situation, you can develop a platoon in this case also. Then a platoon can take care of all the things of the relative positions. Well, this is one of the things during one of our visit at the Robo Center. Okay. Now, yesterday I told you about dead reckoning inputs. Okay. So, you can use a GPS and a dead reckoning combination that is used in automobiles, and there are many companies, Pipe Health Monitoring, which are claiming that they use GPS for the positioning of the system, but wherever you do not get the signal of the GPS, there you use a heading sensor, okay, which can typically use the input from, say, suppose odometer signal. Okay. Odometer gives you the distance measurement, okay, and the direction you can use some sensing. So, using this from the last point of GPS, you know how far you have travelled. So, that can be used as a combination, a GPS plus a dead reckoning system. The other way is to use the optical sensing. Okay. Now, what are the optical sensing generally that we will be able to use? Photoresistor, photovoltaic and photodiodes, and photoemitters. Of course, the optical fibers would come as a very special case in the system. So, the first photoresistor system is what we talked about, the Ldrs, okay, where if there is a change of the light intensity, there is a change of resistance. Okay. So, depending on the change, you can actually measure, and in some cases like cadmium sulphide, the resistance will actually drop down, that means it has a negative coefficient of Ldr, whereas in some cases you will get a positive coefficient, okay, for some materials. So, there are various types of Ldrs that you can make, and through that you can actually change, you can check that what is the change of the light intensity in the system. And many times what you can do is that you can have a reference Ldr with you, so that instead of using directly one Ldr, what is the differential change that is happening in the system. Okay. Now, this is a technology that we are now using, right, in the form of the damage detection itself, because we say that if you have a light emitter and if you have a damaged area, then the reflection level will be different than a non damaged area. So, hence by comparing between the two, you can actually find out that what is the extent of the damage, right. What we may also think of is to use a parallel Ldr, okay, as a reference signal continuously, so that you do not determine the absolute change, but you actually determine the differential between the two. I think that could be a better idea in this context. The other one is photoemitters. Okay. So, in case of photoemitters, what we do is that we have two electrodes, and in between there is the light which can actually change the flow of current between the two electrodes. Okay. So, there are some specific carrier mediums that are very sensitive to the photo emission. Okay. So, for example, if you use nickel and cesium, and then you pass this current, and then depending on the level of the light, you will actually get a change in terms of the current intensity. And this is generally used in series with a resistor and a supply voltage of 25 to 100 volt, not a very high one. The thing is that UV, it is easy to sense this way, changing the UV range, but in the infrared it is very difficult. So, hence inside the pipelines with the darkness, this could be difficult to actually use. You can think of photomultipliers. Okay. For example, something like dinodes, okay, which actually every point inside these dinodes, when it is hitting, it is actually multiplying the photo electron, the light induced the photon generation, and hence it can work like a photo multiplier, and then the signal level could be quite high, and in the infrared level also you may be able to use, provided you use a photo multiplier. Then the other way you can do is by having a photoelectric sensing system. So, in most of the cases we use, for example, the light emitting diodes, okay, and these LEDs, they can be used as various levels, for example, green, blue, blue green, yellow, red or infrared light level. Now, they work in a directional sense. Okay. So, whenever the current is passing in a particular direction, then only the light gets emitted from the system. So, you can actually develop a system which is directionally dependent, and accordingly the light will be blown whenever it is flowing in that particular direction. So, that is what the LEDs you can develop, and there are various colored LEDs. In fact, the colored LEDs are important for us now, because from the corrosional point of view, we are thinking that the various types of corrosions may have various types of a specific type of a LED which will be more sensitive to a particular corrosion. So, we can think of a colored LED system. The last one in this grade is actually using various types of laser sources. For example, we are talking about laser profiling in a opposed mode, in a retroreflective mode, proximity mode or background suppression mode. So, for example, this is one of the opposed mode, where you have an emitter and you have a receiver and you have an object in between. Now, depending on the positioning of the object, this reception is happening. If it infringes, if it does not come, then there will be a light that will be passing. So, if you have two parallel systems, that can be used. You can have this in the form of a retroreflective mode, where the object itself has a retroreflector in it. Okay. So, whenever there is a presence of an object, then the same system can work as an emitter as well as a receiver. It can work in a proximity mode. Okay. So, for example, the presence of an object actually creates the change in terms of divergence on convergence, or it can work in terms of background suppression. That means, the light is actually reflected from the background, and whenever that background light intensity is changing because of the presence of the object, then you can detect that there is the object that is coming in between. So, the position of the object gets detected. A very similar thing is also done in the infrared sensing level as well, where you can have a transmitter and a receiver, and if there is a presence of a particular strip, for example, which stops the infrared or which absorbs the infrared, then the receiver will not get a signal. Thus, you can detect that whether this particular object is present or not. And by having a encoder type of a block of these things, you can actually determine the relative positions of the system. So, here is a emitter reflector system which can work in a pulse modulated form also. Okay. And then the modulation of the signal with the help of things like LED emitters or phototransducer devices, that can be used. So, here it is not the intensity, but the modulation of the signal which can be controlled with respect to the presence of the object itself. So, that is another way of controlling the system. Now, finally, we are talking about optical fibers, right. So, optical fibers is another one sensing technology that we can think of using, which we have not used so far. What happens in an optical fiber? It is actually the light which gets carried. So, that means, you have an electrical signal and then you convert it to light, and let there be a total internal reflection, and then at the other end you convert the light to electrical signal back again, and then you see what is the change that it is subjected to. That is the technology. You can do it in a single mode fiber, where there is only one light path, or you can do it in a multi mode fiber. That means, some light is traveling straight and some light is getting reflected. So, hence you actually get light travelled as various pathways separated between each one of them. So, something like typically between 850 to 1300 nanometer, one can use this kind of optical fiber based system. Now, here we can think of either a glass fiber based optical fiber or a plastic polymeric optical fiber. The advantage of the glass fiber is that in the visual range it is very active, as you can see. It has a wider bandwidth in comparison to the plastic fiber. Plastic fiber has really, it degrades the performance beyond 900 or so. Okay. So, that is one point, particularly the infrared region where we are interested more. Plastic fiber is less sensitive with respect to the glass fiber. However, there are some advantages of plastic fiber also. One is that they survive well under repeated flexing. Okay. So, it is more robust. Okay. Glass fibers being very brittle, you may not be able to use it many a times. And the plastic fiber absorbs certain bands of light wavelengths, okay, including the light mostly from the infrared LEDs. So, you would always require a visible light source for such a system. So, this is kind of a constraint in case of a plastic fiber system, and also they are less tolerant of temperature extremes and chemicals and solvents. Okay. So, you need some sheathing, for example, some polypropylene, Teflon or nylon you need to have as a coating for the plastic optical fibers. So, whenever you are using this kind of a system as an optical fiber, there are various modes in which you can use it. For example, you can use it in terms of change of refractive index, you can use it as a change of modal conversion, you can use it as a change of what you call the intensity change in the system. That means, the loss that comes out of the system. And in each one of these case, it works as a beautiful sensor, provided it is subjected to measurements like temperature, stress, strain, rotation, electric field, magnetic field, etc. In fact, the interesting part is that anything that hampers the flow of the light can be used back as a sensing device. Okay. So, that is what is the good part of the optical sensor. It is really very kind of a wide in terms of application. Now, you can think of using this as an extrinsic fiber optic sensor. That means, you have a light source and you have an environment here. Okay. If there is a corrosion, then the source of light gets affected and hence the output will change. You can also use it as an intrinsic sensor. In the intrinsic case, what happens is that you develop intrinsically things like micro bends in the system. Okay. And this kind of changes, or sometimes we actually make gratings in the system, and this kind of changes can get affected by the change of the environment. That is the intrinsic type. So, for example, in this case there are micro bends in the system and there is a pressure change, and that changes the curvature of each of the micro bends, and hence it will affect the intensity, the frequency, etc. So, that is the way of using intrinsic type of this kind of sensor. So, more or less I have tried to provide you all the various types of sensors that are conventionally used off the shelf for these kinds of sensing, like the sensing in terms of direction, the sensing in terms of displacement, velocity, acceleration, position, etc. Okay. Thank you. So, if you have some questions, we can discuss. Yeah. Yeah. Difference between the two, correct. See, accuracy is actually with respect to any standard measurement. Okay. Suppose you have a standard measurement of a distance which is something like 10 millimeter. Now, if my sensor can reach 9.99, then my accuracy is 0.01. Precision, on the other hand, is in terms of repeated measurements. Okay. Every time when the sensor is used, the robust sensors will not lose its values, but these non-robust sensors will gradually give you less and less accurate results. That is what is the precision. Yeah, Chandan. Light is associated with? Yeah. No, are you talking in terms of Ldrs? Light detecting resistors. Yeah. Correct, correct. Yeah, yeah. That is different. That is for the optical fiber. There the angular distance does not matter much, because you are going for a total internal reflection inside. Only thing that you can do there is that you can choose a reflective surface which can actually change it from a modal, the modes. For example, it can change it from single mode to multiple modes, depending on the angle of reflection. Okay. For Ldr, yes, you are right that the incidence angle change is going to change the the Ldr's effectiveness, but then you preset that angle. For example, when the system that Himanshu has devised, the LED Ldr combination, there the way the light is going and it is reflected back for any regular reflection, that is predetermined, and anything irregular, that is why can be sensed from that system. Can you think of optical fiber in terms of this kind of damage detection, non-contact way we have to think of it. Okay? We cannot of course think of contact with the pipe, but that is something. See, for example, I am telling you that we have talked about Pvdf sensor, correct. So, what does the Pvdf sensor does? The sensor itself touches the pipe, the tip of it, and then the change of dynamic strain it converts to voltage. Now, instead of a Pvdf converting that strain to voltage, suppose we have these optical fiber based small micro benders, right, and then that can also detect at a very high accuracy level. Only thing is possibly it is at a low frequency level. We can use this optical fiber, right. Yeah. So, in the Lego toolkit we have this small optical fiber that they always give. We can use it as a micro bender, right, like a small circular patch, and then use it all around the probe. And you should have a LED and splicing, basically you should have a LED and a receiver, and that LED and the receiver can be actually situated inside the pipe health monitoring robot itself. So, the light is getting passed, and whenever there is a change of shape, you are actually determining that change of how much bend it has taken. So, please think of it. I just while doing this I thought, why have we overlooked that part. Okay, so that is where we will end, and then let us take a small break.